If you destroyed every book written in ancient Egypt, burned every papyrus scroll, erased every carved hymn and royal decree, you would still know how they thought, because they left something far more revealing than words. On the edge of the Sahara, rising from the limestone bedrock of the Giza Plateau, stands a structure so vast it bends the horizon around it. For over 4.5 millennia, the Great Pyramid of Giza has dominated the desert skyline. Wind has stripped its casing, empires have looted its stone, earthquakes have tested its mass. But no fire has ever touched what it truly preserves. There is no instruction manual inside, no engineering scroll tucked behind granite blocks, no blueprint etched in secret chambers. And yet it encodes something undeniable, not messages, methods, not mythology, execution. We have been trained to look at monuments as statements of belief. Temples speak of gods, cathedrals proclaim salvation, palaces whisper of power. So we look at the pyramid and assume the same, a tomb, a symbol, a ladder to the afterlife. But what if that assumption blinds us? What if the pyramid is not a monument to belief, but proof of disciplined measurement applied at civilizational scale? Because here is the quiet shock. The interior of Khufu's pyramid is almost completely silent. Step inside, and you will not find walls alive with hieroglyphic narrative. No celestial diagrams spiral across the granite of the king's chamber. No creation myth unfolds along its corridors. Unlike the painted tombs of later dynasties, this structure contains almost nothing that explains itself. It doesn't tell you what to think, it forces you to measure. And that silence, that deliberate absence of explanatory text, is where our journey begins. For generations, we have wrapped this structure in story. A tomb for a god king, a monument to divine authority, a relic of solar worship. Some have insisted it encodes hidden knowledge of the stars. Others whisper of lost civilizations, vanished technologies, even visitors from beyond Earth. The speculation itself tells a story. When faced with something extraordinary, the human mind reaches for myth. But myth is unnecessary here. The true mystery is stranger and far more demanding. Because the pyramid does not hide secrets in symbols. It reveals them in tolerances. Consider what stands before us. Built around 2550 BC under Pharaoh Khufu of the 4th dynasty, this structure once rose to approximately 146.6 meters, nearly 500 feet, making it the tallest man-made object on Earth for nearly 4,000 years. Its base stretches roughly 230 meters on each side, 13 acres of stone, leveled and squared. And yet scale is not its most unsettling feature. Precision is. Its base is leveled to within mere millimeters across an area larger than 10 football fields. Its sides are aligned to true north with an error of only about 3 to 4 arc minutes, a fraction of a single degree. Its corners form near perfect right angles. This was achieved without steel, without lasers, without digital instruments, without written engineering manuals that have survived. So we must ask, what is being demonstrated here? Because demonstration is different from decoration. Decoration expresses belief. Demonstration expresses capability, and capability requires discipline. Inside the pyramid, the passage is narrow with purpose. The grand gallery rises in corbelled precision. The granite beams above the king's chamber, some weighing more than 50 tons, are positioned with deliberate intent to redistribute stress. The structure does not merely rise, it manages forces. Gravity is not ignored, it is anticipated. The pyramid does not defy nature, it collaborates with it. That distinction matters. If this were merely symbolic architecture, approximate alignment would suffice. A few degrees off north would still point generally toward eternity. A slightly uneven base would still impress the eye. But the builders did not aim for generally, they aimed for exact, and exactness is expensive. It demands measurement systems, it demands stable reference frames, it demands repeatability across decades. This is where the misunderstanding begins to fracture. We call it a tomb. And yes, it likely functioned as one, but tomb is a category. It does not explain the execution. Thousands of tombs exist across Egypt. None approach this level of geometric control. We call it a religious monument. Yet religion does not require sub-arc-minute astronomical alignment. Faith does not demand millimeter leveling across 13 acres of bedrock. We call it symbolic. But symbolism does not require statistical improbability. What we are seeing is not excess devotion. It is applied knowledge. The pyramid communicates through constraint, constraint of angle, constraint of orientation, constraint of level, constraint of mass distribution. It is a structure that reveals what happens when a civilization treats reality, not myth, as the primary authority. And here is the unsettling implication. If every written record of ancient Egypt vanished tomorrow, this structure alone would tell us that its builders understood geometry, error correction, long-term planning, material science, and coordinated labor management at extraordinary scale. You cannot fake this level of execution. You cannot accidentally align a 230-meter structure to true north within a fraction of a degree. You cannot maintain slope consistency across millions of stone blocks without standardized ratios. You cannot place multi-ton granite beams into a relieving system without anticipating compressive forces. The pyramid is not a message carved in stone. It is a process frozen in stone, and processes reveal mindset. So what mindset does this reveal? A civilization that believed measurement mattered. A culture that stabilized its baselines before raising its monuments. A society that understood that alignment to earth, to gravity, to geometry was not symbolic decoration, but structural necessity. This is our call to adventure, because if the pyramid does not store knowledge in words, if it does not encode secret prophecies or hidden star maps, then what exactly is it showing us? It is showing us how knowledge was applied. And that may be far more radical than any lost scroll, because writing can exaggerate, myth can distort. But stone does not lie about tolerances. Stone remembers whether your angle was true. Stone records whether your baseline drifted. Stone exposes whether your system held. And for 4,500 years, this structure has been quietly asserting one fact. The people who built it were not merely believers. They were disciplined measurers. And if that is true, then the pyramid is not a relic of superstition. It is evidence of a worldview grounded in structure, constraint, and reality itself. Which leaves us with a far more provocative question. If this monument is not storing knowledge, if it is not speaking in hieroglyphs, if it is not encoding myth, then what precisely is it demonstrating about how a civilization thinks? And more importantly, what does it reveal about us? Around 2550 BC, on a plateau of wind-scoured limestone west of the Nile, construction began on what would become the most exacting stone structure of the ancient world. The Great Pyramid of Giza rose to an original height of approximately 146.6 meters, nearly 481 feet. For almost 4,000 years, nothing built by human hands would surpass it. Its base extends roughly 230.4 meters on each side. That is 756 feet, each edge long enough to stretch across 2 modern city blocks. The footprint covers about 13 acres, enough space to hold St. Peter's Basilica with room to spare. The mass is estimated at roughly 6 million tons. Approximately 2.3 million stone blocks compose the structure, though the true number may vary depending on how one counts internal packing stones and casing. Average blocks weigh between 2.5 and 15 tons. Granite beams within the King's Chamber reach 50 to 70 tons. These numbers are familiar. They appear in textbooks, documentaries, tourist brochures. But numbers become numbing when repeated. So pause. 6 million tons of material quarried, transported, positioned, and set without steel cranes, combustion engines, or hydraulic systems. 230 meters per side, squared and oriented without satellite surveying. A vertical rise of nearly 1.5 football fields stacked into the sky, completed within roughly 2 decades. Scale alone is impressive, but scale alone is not rare. The Roman Colosseum is vast. The Great Wall of China is vast. Modern dams dwarf ancient masonry in sheer volume. Humanity has always been capable of building large when motivated. Large is a function of labor and time. Precision at scale is something else entirely, because when structures grow, error compounds. If you misjudge level by a single centimeter over 1 meter, the deviation is negligible. Over 200 meters, that same proportional error becomes catastrophic. If your angle drifts by a fraction of a degree at the base, by the summit it becomes visibly skewed. Scale amplifies imprecision, and this is where the Great Pyramid ceases to be merely large. Its base is level to within millimeters across the entire 13-acre footprint. Let that settle. Across 53,000 square meters of bedrock foundation, the variation in elevation is astonishingly small. Modern surveys indicate discrepancies measured in mere centimeters at most, and likely even less in its original state before erosion and stone removal. To achieve that, the builders had to establish a consistent horizontal reference across an enormous surface. Water leveling trenches may have been used. Perimeter strips cut into bedrock suggest systematic calibration. Whatever method was employed, it required one thing above all: a stable baseline. Now consider orientation. The pyramid's sides are aligned to true north with an error of approximately 3 to 4 arc minutes, roughly 0.05 degrees. To visualize this, imagine standing at the base and sighting along one edge. If that line extended for a mile, it would deviate from perfect north by only a few feet. This level of alignment is comparable to modern surveying accomplished with optical instruments. Yet this was achieved in the 3rd millennium BC. This is not approximate cardinality, it is astronomical alignment. And then there are the corners. The 4 base corners form near-perfect right angles. Deviations from 90 degrees are extraordinarily small. Statistical analyses suggest the angular accuracy approaches 1 part in 10,000. That is an angular precision often under a single arc minute. This is not brute force stacking of stone. This is controlled geometry expressed through mass. If the pyramid were merely large, one could attribute it to centralized labor and political will. A powerful pharaoh, thousands of workers, decades of effort. But brute force cannot produce consistent right angles across 230-meter baselines unless the angles are measured, checked, and rechecked. Brute force cannot maintain level across 13 acres unless horizontal reference is continuously verified. Brute force cannot align a structure to Earth's rotational axis within a fraction of a degree unless the sky itself has been used as calibration. We must separate 2 different achievements. Moving stone is an engineering challenge. Maintaining geometric integrity across millions of stones is a systems challenge. The pyramid's sides differ in length by less than 20 centimeters across 230 meters. That is a variation of less than 1/10%. Consider modern construction tolerances. Even today, deviations accumulate quickly without laser guidance and digital modeling. Ancient builders did not possess CAD software or total stations, yet the final structure reveals internal coherence. The slope angle of the pyramid faces, approximately 51 degrees 51 minutes, remains remarkably consistent from base to apex. That consistency required a maintained ratio of rise to run across the entire construction process. You cannot set that angle once and hope it persists. Each successive course of stone had to respect the established geometry. Each block had to conform to a system already in place. This is where scale transforms from spectacle to evidence, because scale multiplies opportunity for error. 2 million opportunities for drift, 2 million opportunities for inconsistency, 2 million opportunities for cumulative deviation, and yet the finished structure holds its lines, it holds its orientation, it holds its proportions. If one were to erase every story about divine kingship and funerary rites, the geometry would remain. The tolerances would remain. The orientation would remain. But what does that imply? It implies that measurement was not incidental to this civilization. It was central. The builders did not simply pile stone until a mountain emerged. They imposed a coordinate system upon the earth and then filled it with matter. The pyramid is, in effect, a three-dimensional manifestation of a grid, an abstract framework realized in limestone. And here we cross the threshold, because once we accept that precision at this scale was intentional, we are forced to abandon comforting explanations rooted in symbolism alone. A symbolic monument can be forgiving. A geometric instrument cannot. The Great Pyramid behaves like an instrument. Its base behaves like a calibrated platform. Its sides behave like vectors locked to cardinal directions. Its angles behave like preserved ratios. This is not mythic exuberance, it is controlled execution. And control implies method. Method implies knowledge, not knowledge stored in text. Knowledge expressed in action. The stone does not tell us what they believed about the afterlife. It tells us they could stabilize reference frames across enormous distances. It tells us they could translate astronomical observation into architectural alignment. It tells us they could coordinate labor in a way that preserved geometric integrity for decades. Mass does not explain this. Mass can be gathered. Mass can be moved. Mass can be commanded. But mass does not spontaneously arrange itself into millimeter-level platforms aligned to planetary rotation. Measurement does. And once we see that, the pyramid becomes something far more unsettling than a tomb. It becomes proof that in 2550 BC, a civilization had already mastered something we take for granted: the discipline to bind ambition to geometry, which leaves us standing at the base of 6 million tons of stone with a new and more dangerous question forming in the desert air. If mass does not explain this, if labor does not explain this, if myth does not explain this, then what system of measurement made it possible? Stand at the northern edge of the Great Pyramid of Giza just before dawn. The desert is quiet, the horizon pale. And if you extend your gaze along the edge of the structure, along that immense straight limestone line, you are looking almost perfectly toward true north. Not magnetic north, not approximate north. True north, the rotational axis of the Earth itself. Modern measurements place the pyramid's orientation within roughly 3 to 4 arc minutes of true cardinal alignment. That is approximately 0.05 degrees of error. To understand what that means, imagine a full circle divided into 360 degrees. Divide one of those degrees into 60 arc minutes. The pyramid misses perfection by only 3 or 4 of those minute subdivisions. If its north-south line extended for a kilometer, it would drift off true alignment by only a few meters. This was achieved in 2550 BC. Modern surveyors, using optical transits and calibrated instruments, routinely achieve similar precision. With laser theodolites and satellite correction, we surpass it. But without optical glass, without magnification, without digital reference, to approach that tolerance is extraordinary. And this was not achieved on a small shrine or a modest platform. It was achieved on a 230-meter baseline carved into bedrock. So how? Several hypotheses exist, but one has gained increasing credibility: astronomical observation using a gnomon, a vertical rod, and solar tracking during the equinox. On the equinox, the sun rises due east and sets due west. If one tracks the tip of a gnomon's shadow throughout the day, plotting its arc, the midpoint between the morning and afternoon shadow positions can establish an almost perfect east-west line. From that, a perpendicular yields true north-south, simple in principle, demanding in execution, because the equinox is a moment of balance in Earth's orbit. It occurs when the plane of Earth's equator passes through the center of the sun. Day and night are nearly equal, but determining the precise day of the equinox without calendars as we know them requires careful observation of seasonal cycles. counting days after the solstice, monitoring the sun's declination. This implies sustained astronomical awareness. And yet even this method does not guarantee sub-arc-minute precision unless repeated, averaged, and corrected. Other scholars have proposed stellar alignment using circumpolar stars, particularly those near the north celestial pole at the time. By observing the transit of paired stars across a vertical sighting instrument, the builders could establish a north line with remarkable accuracy. Whether solar or stellar, or a combination, the result is the same. The pyramid is locked to the axis of planetary rotation, not approximately, deliberately. Now pause and consider the statistical improbability of accidental alignment. If one were to randomly orient a square of that size, the chance of landing within a few arc minutes of true north by coincidence is vanishingly small. Even an error of 1 degree would be visually imperceptible to a casual observer. Religious symbolism would not require such refinement. 3 arc minutes is not aesthetic, it is technical, and here is where the revelation begins to deepen. Why align so precisely? Many have argued symbolism, that north represented eternity, the circumpolar stars, the undying realm. That may well be true in a cultural sense, but symbolism alone does not demand this degree of angular control. If the goal were merely to gesture toward the heavens, approximate alignment would suffice. Instead, what we observe is calibration. Alignment at this tolerance transforms the pyramid from monument to reference frame. A structure this large, fixed to true north, becomes an architectural axis, a physical embodiment of planetary orientation. The builders effectively anchored their construction to the rotational geometry of Earth itself. This is not decorative astronomy, it is cosmology operationalized. Civil engineering anchored to celestial mechanics. Because true north is not a direction on a map, it is a line defined by Earth's spin. By aligning the pyramid so precisely, the builders tied their structure to something invariant, the rotation of the planet beneath their feet. And that changes everything. A structure aligned to magnetic north would drift over centuries as the magnetic field shifts. But true north, defined by rotation, remains stable on human timescales. They did not align to a wandering field. They aligned to an axial constant. This suggests a profound respect for stable reference. A civilization concerned not merely with building high, but with building true. Once the base is aligned, every subsequent stone inherits that decision. Every corner, every chamber, every slope derives from that foundational axis. If the north-south line is wrong, everything built upon it compounds the error. So the first act of construction was not lifting stone, it was fixing orientation. Imagine the scene. Surveyors standing on bedrock, instruments simple but carefully crafted, observations repeated night after night or day after day, lines scratched into limestone, corrections applied, consensus achieved. Only when the axis was trusted would the massive endeavor proceed. This is not mythology in action. This is metrology, and metrology, the science of measurement, is the invisible skeleton of civilization. We cannot build bridges without it. We cannot synchronize power grids without it. We cannot launch spacecraft without stabilizing reference frames. The builders of Khufu's pyramid understood this at an architectural scale. They began not with stone, but with alignment, which forces a subtle but profound shift in our interpretation. The pyramid is often described as pointing toward the heavens, but that is backwards. It is fixed to the earth. It does not reach upward randomly. It rises from a stabilized coordinate system tied to planetary motion. This is not mystical longing for the sky. It is geometric obedience to physical reality. The builders did not ask the heavens for permission. They measured them. And once measured, they translated that celestial geometry into stone. The result is a structure whose orientation still aligns with Earth's axis after 4,500 years of tectonic quiet. Wind has eroded its casing, earthquakes have shaken its mass, Empires have risen and fallen around it, but its north line remains, which leads us to the unsettling pivot. Alignment at this level is not expressive, it is structural. It reveals a worldview that valued fixed reference over narrative flourish, a worldview in which stability preceded symbolism. And now we arrive at the question that should trouble us. If this was merely a tomb, if it was only meant to house a king's body and spirit, why does it require sub-arc minute orientation to planetary north? Why does eternity demand calibration? Why does death require alignment to Earth's rotational axis? Mass does not require this. Belief does not require this. Only measurement does. So, what were they really building when they fixed that first line into the limestone of Giza? And what does it mean that thousands of years later, we are still measuring our instruments against the same axis they chose? Before a single casing stone gleamed in the desert sun, before granite beams were hauled into the rising core, before the first course lifted the horizon by even a hand's breadth, there was the ground, not sand, not shifting dune, bedrock. The builders of the Great Pyramid of Giza did not simply clear a patch of desert and begin stacking stone. They carved into the limestone plateau itself, cutting channels, flattening ridges, integrating a natural rock knoll into the pyramid's core. The structure does not sit on the earth, it is keyed into it, and here is where the difficulty intensifies. To align to true north is one challenge. To maintain level across 13 acres of irregular bedrock is another entirely. The pyramid's base measures roughly 230.4 meters per side. Across that immense square, the variation in elevation is astonishingly small, measured in mere centimeters, likely even less before erosion and stone removal. For comparison, modern construction sites rely on laser levels and digital surveying to maintain comparable tolerances. Even slight deviations over such distances can create visible slope or structural imbalance. Yet this was achieved in 2550 BC. How? One of the earliest serious proposals came from the British surveyor and Egyptologist Flinders Petrie. Working in the late 19th century, Petrie suggested that the builders may have cut a network of shallow trenches into the bedrock perimeter and filled them with water. Water, obeying gravity, finds its own level. By marking the water line along the trench walls, workers could establish a consistent horizontal reference across the entire footprint. Elegant, simple, physically grounded. If true, this implies not guesswork, but deliberate exploitation of natural law. Later investigations led by Egyptologist Mark Lehner revealed cut perimeter strips around parts of the pyramid's base, narrow leveled zones carved directly into the limestone. These strips suggest that leveling may have been achieved progressively along the edges rather than across the entire area at once. Instead of flattening 13 acres simultaneously, the builders may have established precisely leveled boundary lines first, defining the square, and then worked inward. That changes the picture, because it implies staged control. Define the perimeter, lock the baseline, then fill the interior to match. More recently, engineer Glenn Dash applied modern statistical tools to reconstruct the pyramid's original baselines. By using linear regression analysis on surviving casing foundation points, Dash demonstrated that the builders likely established long, straight reference lines and corrected deviations systematically. Not eyeballing, not rough alignment, but iterative correction. Now consider the numbers. The four sides of the pyramid differ in length by less than 20 centimeters across 230 meters.
20 centimeters over 230 meters is a deviation of less than 0.1%.
But here is the more intriguing detail. The angular deviation, how close the corners are to perfect 90 degrees, is even smaller proportionally than the side length variation. In other words, the angles are more precise than the lengths. That is counterintuitive. If you measure lengths imperfectly, angles usually suffer. If your baseline wavers, your corners drift. Yet here we see something different: extraordinary angular fidelity. This suggests that angle construction was not incidental, it was prioritized. The builders appear to have been more concerned with preserving right angles than achieving identical side lengths. Why? Because angles define structure. Lengths can vary slightly without catastrophic consequence. But if your corners are not true right angles, your entire geometry destabilizes as you rise. This brings us to geometric inference. One proposed model, sometimes referred to as ATMR, Advanced Triangle Measurement Reconstruction, suggests that the builders may have used large-scale isosceles triangles and extended perpendicular methods to establish right angles with remarkable accuracy. Imagine laying out a baseline. From that baseline, construct equal-length arms to form a triangle. Where those arms meet defines a point that enforces geometric consistency. Scale this method up using measuring rods, not stretchable chords, and one can achieve right angles accurate to astonishing tolerances. Chords, after all, stretch. Wooden rods cut across the grain do not stretch significantly. The Egyptians were aware of this. Evidence from other sites shows they used rods in metrological tasks. Chords could expand by up to 2% depending on humidity and tension. Over 230 meters, that error would be disastrous. So they compensated. Measurement was not casual, it was disciplined. Now imagine the scene: surveyors on bedrock, rods laid end to end, points marked, angles tested using triangle constructions, deviations shaved down, lines rechecked at dawn and dusk when shadows sharpen. And all of this before the first massive block was set, because once the first course is laid, error compounds vertically, the base must be true. Here is what makes this leveling almost unbearable to contemplate. It had to remain true for decades. Construction of the Great Pyramid likely spanned roughly 20 to 25 years. Over that period, thousands of workers rotated in and out. Leadership may have changed, political priorities may have shifted, yet the baseline did not drift. The original alignment and leveling had to be preserved across an entire generation. That implies record-keeping of measurements, perhaps not written in manuals, but embodied in master surveyors. It implies institutional continuity. Someone, or some group, guarded the geometry. They checked it, they enforced it, they corrected deviations before they became visible, because if the baseline slipped by even a small margin early on, by the time the pyramid reached half its height, the error would be undeniable. Instead, what we see is coherence, a structure whose corners meet the sky in disciplined convergence, a structure whose footprint remains square within extraordinary tolerance. This is not the romance of ancient mystery. It is the sobriety of systems control. Leveling 13 acres to near uniform elevation without steel tools or modern instruments is not an act of devotion. It is an act of sustained calibration. And calibration requires authority, authority over method, authority over workers, authority over time, which forces us into the inmost cave of this argument. Because leveling is not glamorous. Alignment to the stars captures imagination, towering height inspires awe. But leveling is discipline. It is invisible work. It is the quiet enforcement of horizontal truth. It says, gravity is the law. It says, error will not accumulate unchecked. It says, no stone will rise unless the base is verified. And this is where the pyramid ceases to be a monument and becomes a mirror. It reflects a civilization that stabilized its ground before it reached for the sky, which raises a question that is both technical and philosophical. This degree of leveling requires process control not for a moment, but for decades. It requires standards that do not drift. It requires measurement systems that outlive individual workers. It requires a culture that values baseline integrity above speed. So who maintained the baseline? Who ensured that the first horizontal reference carved into bedrock remained authoritative 20 years later? Who guarded the right angles when the desert wind erased footprints and generations turned over? Because without that continuity, 6 million tons of stone would have betrayed them. And yet, it did not. long before wind stripped it bare, long before earthquakes loosened its skin, long before medieval builders quarried its outer shell for distant cities. The Great Pyramid of Giza did not look like it does today. It did not rise as a stepped mass of exposed core blocks. It was smooth, blinding, encased in fine white limestone quarried from Tura across the Nile. A dense, high-quality stone composed almost entirely of calcite. Under the Egyptian sun, that casing would have reflected light like a polished mirror. Ancient travelers described it as luminous, a geometric mountain of light. But beauty was not its primary function. Precision was. The casing stones at the base, those few that remain in situ, reveal something extraordinary. The joints between them average around half a millimeter. Half a millimeter. That is thinner than a credit card, thinner than the edge of a fingernail, between blocks weighing up to 15 tons. These were not decorative veneers placed casually against a rough core. They were cut with planar surfaces so exact that when pressed together, they formed seams nearly invisible to the eye. And here is the crucial detail. These stones were not simply laid flat. They were cut at an angle. The pyramid's faces rise at approximately 51 degrees and 51 minutes. That slope is not approximate. It is consistent. From base to apex, the inclination maintains its ratio with remarkable fidelity. Now imagine the challenge. A casing stone must sit flush against the stone below it. Its bottom surface must match the established slope. Its side surfaces must align with adjacent stones horizontally and vertically. Its outer face must contribute to a continuous planar surface extending over 230 meters. If even a few casing stones deviate in angle, the entire face begins to ripple. The geometry telegraphs error immediately. A misalignment of a few millimeters at the bottom becomes centimeters by mid-height. By the time you approach the upper courses, the distortion would be visible. But when the casing was intact, it formed an almost perfectly smooth surface, a continuous geometric plane rising in luminous symmetry. This is not ornamentation. It is geometric enforcement. The casing stones functioned as the outer expression of the pyramid's internal discipline. They locked the slope. They defined the plane. They made deviation visible. Without them, small errors in the core could hide. With them, every angle had to obey the original ratio. In this sense, the casing acted like a calibration surface. Think of a modern machine tool. Its external housing may appear simple, but the machined surfaces inside are cut to precise tolerances to ensure alignment and performance. In the pyramid, the polished casing was the machined surface. It was not symbolic radiance. It was structural truth. Each casing block had to be shaped so that its interior side matched the stepped core behind it, while its exterior face conformed exactly to the intended slope. This required anticipatory cutting. You cannot carve such precision after placement. The stone must arrive ready. And because the pyramid rises in courses, each successive layer depends on the accuracy of the one beneath it. You cannot correct a flawed slope halfway up a face without dismantling entire sections. So the discipline had to be relentless. At the base, the slope angle is established. Each course above must replicate it, 51 degrees and 51 minutes, not 52, not 51 and a half. The ratio between vertical rise and horizontal run had to remain consistent across hundreds of layers and millions of stones. This is where the argument sharpens. If the pyramid were merely a tomb, approximate smoothness would suffice. A few irregularities would be invisible from ground level. The human eye forgives imperfection at distance. But the builders did not rely on visual forgiveness. They imposed geometric rigor. Half-millimeter joints between 15-ton blocks are not achieved by chance. They require flatness of surface. They require control over cutting tools. They require repeated checking. Copper chisels, dolerite pounders, abrasion with sand and water. Primitive by modern standards. Yet the result approaches machine-like fit. And here is the subtle but devastating implication. To achieve an average joint gap of 0.5 millimeters once would be impressive. To achieve it across thousands of stones is evidence of system. Each casing block was not a singular masterpiece crafted in isolation. It was one iteration in a sequence, one disciplined repetition in a process that tolerated no drift. And because these stones formed the visible exterior, they acted as public proof of that discipline. The pyramid did not whisper its precision, it broadcast it in light. Imagine the moment when the final casing stones were set near the summit. The entire structure would have gleamed, a seamless geometric form rising from leveled bedrock, aligned to true north, locked at a constant slope. No bulges, no visible seams. A single idea expressed in stone. And that idea was not myth. It was constraint. Constraint of angle, constraint of surface, constraint of tolerance. Polish is often mistaken for luxury. Here, polish was enforcement. If the slope deviated, the casing would not sit flush. If the base were uneven, the lower courses would reveal the error. If the angle drifted, the face would not converge symmetrically at the apex. The casing forced the core to obey geometry. This is execution discipline at civilizational scale. It is easy to romanticize the hauling of stone, the laborers straining under the desert sun. Harder to appreciate is the quiet act of checking a surface against a straight edge, of grinding until planes meet, of rejecting a block that deviates from standard. Precision is not dramatic, it is patient, and patience multiplied across decades becomes culture. Now consider the psychological implication. A society willing to invest such effort into half-millimeter joints is not improvising, it is enforcing standards. Standards require agreement. Agreement requires authority. Authority requires stability. The polished casing was not merely the skin of a monument, it was the visible evidence that a baseline had held. Now, achieving that precision once is an achievement. Achieving it twice suggests competence. Achieving it thousands of times suggests systemized knowledge. You cannot rely on inspiration. You cannot rely on luck. You cannot rely on a single genius artisan. You must replicate tolerances block after block, course after course, year after year. And this is the revelation hidden in limestone. The pyramid does not show us a single moment of brilliance. It shows us repeatable control. You cannot achieve this once. You must achieve it thousands of times. And once you recognize that, the question changes. It is no longer, how did they build something so large? It becomes, what kind of civilization sustains that level of precision, unbroken, for decades? And who ensured that every stone, from the first at the base to the last near the sky, obeyed the same unyielding geometry? Enter the pyramid. Leave behind the blinding geometry of its vanished casing. Step through the descending passage, narrow, angular, deliberate. The air cools, the sound changes. Limestone encloses you on all sides. And almost immediately, something becomes clear. The interior is not chaotic. It is not a hollow mountain carved after the fact. It is structured, measured, composed with the same discipline that governs the exterior. Deep within the Great Pyramid of Giza lies the King's Chamber, a rectangular space constructed entirely of red granite quarried from Aswan, more than 800 kilometers to the south. Each granite block weighs between 25 and 40 tons. The beams forming the ceiling and the layers above reach between 50 and 70 tons apiece. Granite is far harder than limestone. It is difficult to quarry, difficult to shape, difficult to transport. And yet here, in the geometric heart of the pyramid, it is positioned with quiet authority. The chamber itself is aligned almost perfectly with the pyramid's central axis. Its walls are straight, its corners are true, its floor is level. This is not accidental placement, it is centralization. The King's Chamber does not wander within the mass. It is not slightly offset, as one might expect in a structure built by approximation. It sits on the center line, which means the center line was known and preserved. Now look above the chamber. 5 relieving chambers, low granite spaces stacked atop one another, separate the chamber ceiling from the immense weight of stone rising above. The beams in these chambers are colossal, laid horizontally in the lower relieving spaces, then capped with angled limestone blocks in the final chamber to divert compressive force away from the chamber ceiling. This is stress management. It is architectural foresight. Without these relieving chambers, the weight of millions of tons pressing downward could have fractured the chamber below. The builders anticipated gravitational load. They did not wait for collapse to teach them. They engineered around it. Consider what this implies. To construct relieving chambers, one must understand that stone under compression transmits force downward. One must understand that distributing that force across angled surfaces reduces concentrated stress. This is not symbolic architecture. It is structural engineering. And the granite beams themselves, some weighing more than modern trucks, had to be lifted dozens of meters above ground level and positioned precisely. There is no margin for improvisation here. You cannot adjust a 70-ton granite beam casually once it is set. It must fit. Now turn to the so-called air shafts extending from the king's chamber and the queen's chamber below. These narrow channels, roughly 20 centimeters square, angle upward through the pyramid's mass at specific inclinations. The southern shaft of the king's chamber rises at approximately 45 degrees, the northern shaft at roughly 32 degrees. They are not randomly bored. Their angles appear intentional, potentially aligning at the time of construction with particular stars, including those associated with circumpolar constellations and Orion. Whether one interprets these alignments symbolically or functionally, the precision remains. A shaft cut through dozens of meters of stone must maintain consistent angle and direction. Even a small deviation would cause it to emerge in the wrong location. The shafts terminate originally at the exterior surface, which means their angle had to be calculated in advance, from interior chamber to exterior face, before the surrounding mass was fully constructed. This requires 3-dimensional planning. You cannot carve such shafts by guesswork once the structure is complete. They were embedded into the design from the beginning. And then there is the rock itself. The pyramid was not built atop perfectly flat terrain. At its core lies a natural limestone knoll, a raised outcrop integrated directly into the structure. Rather than removing it entirely, the builders incorporated it. The descending passage cuts into this natural rock. The subterranean chamber is carved directly from it. The knoll becomes part of the pyramid's mass. This is not crude adaptation, it is strategic integration. Removing the knoll would have required enormous additional labor and risked destabilizing the foundation. Instead, they shaped the geometry around it, locking natural bedrock into the engineered design. The pyramid is not imposed blindly upon the earth. It is interlocked with it. Interior and exterior obey the same system. Alignment to true north is preserved internally. The passageways reflect the same cardinal logic as the outer faces. The center line is maintained from base to chamber to apex. There is no sense of last-minute revision, no visible compromise, no evidence of improvisational correction. The internal geometry mirrors the exterior discipline, which is perhaps the most telling detail of all. It would have been easier to focus precision on the exterior, the visible surfaces that proclaim power to the world. But the builders maintained discipline even in hidden spaces. The relieving chambers above the king's chamber were not meant to be seen. They were sealed within stone, invisible for millennia until explorers uncovered them. Yet their construction is meticulous. Their beams are straight, their angles deliberate. This is the mark of a system that does not relax when unseen, and that perhaps is the clearest indicator that we are not observing ritual improvisation. We are observing applied method. The pyramid's interior does not feel like a hollowed monument carved after construction. It feels like a structure built around predetermined geometry. The center was known before the sides rose. The chambers were located before the outer courses climbed skyward. The shafts were angled before the mass enclosed them. This required a master plan, not a sketch in sand. A conceptual model held and enforced over decades, and here the tension tightens. Because construction of the Great Pyramid likely lasted around 20 to 25 years. Long enough for children to become adults, long enough for master craftsmen to age, long enough for political winds to shift. Yet the interior geometry shows no discontinuity. No change of design philosophy mid-construction, no drift in centerline, no abandonment of alignment. This implies continuity of knowledge, continuity of authority, continuity of measurement standards, which brings us to an unsettling realization. A single architect could conceive such a design, but no single human could supervise every stone for 25 years without succession. The pyramid's internal coherence suggests something larger than individual brilliance. It suggests institutional memory, a system capable of preserving geometry across time. And now we stand at the threshold of a deeper question, because lifting granite beams is impressive, carving angled shafts is impressive, integrating a rock knoll into a 6 million-ton structure is impressive, but sustaining a unified geometric plan from foundation to apex, that is something else entirely. It implies planning beyond immediate necessity, planning that assumes continuity, planning that expects the future to hold. And that leads us to a haunting conclusion. This structure required foresight extending beyond any single season, beyond any single campaign, perhaps beyond any single lifetime, because to design internal chambers aligned to a central axis, to embed shafts at precise inclinations, to distribute gravitational stress through hidden relieving systems, all before the final stone is placed, is to commit to a vision that outlives the hands that begin it. And so the question presses in, heavier than granite. This required planning beyond any single generation's lifespan. Who conceived it? And more importantly, what kind of civilization assumes it will remain stable long enough to finish such a design? Every discussion of the Great Pyramid of Giza eventually circles back to a familiar estimate. Roughly 20 to 25 years of construction, most often attributed to the reign of Khufu. Whether the exact number was 18, 23, or 27 matters less than the implication. This was not a seasonal project.
This was not a burst of effort.
This was a generational commitment measured in decades, and decades introduce a problem more difficult than quarrying stone. Time destabilizes precision. Imagine if, 5 years into construction, a new survey team re-established north slightly differently. A new foreman interpreted slope angle marginally off. A replacement crew set courses based on worn or altered baselines. The error would compound. At 10 meters, a slight deviation is invisible. At 100 meters, it becomes structural. At 146 meters high, it becomes catastrophic. But the pyramid shows no evidence of progressive angular drift. Its geometry is coherent from foundation to apex, which means something remarkable occurred. The builders prevented measurement drift across decades. Human systems are unstable, leadership changes, administrators die, priorities shift, court factions compete. Yet the pyramid's geometry suggests no interruption in reference standards, no reset in measurement method, no visible shift in planning philosophy. That implies that the measuring system was not personal, it was institutional. Not dependent on one architect, not dependent on one vizier. It survived the flow of political time. This is the deeper achievement, not the lifting of stone, the stabilization of process. Earlier, we considered that the pyramid is fixed to Earth's rotational axis, aligned not symbolically but physically to true north. Now we see a parallel. Just as the structure was anchored to a planetary reference frame, the civilization itself had to anchor its procedures to something stable. A consistent cubit length, a consistent angular method, a consistent baseline definition. Without that, the pyramid dissolves into accumulated error. So what does this imply? It implies that Old Kingdom Egypt had standardized measurement tools, calibration methods, redundant verification systems, and hierarchical quality control. Not modern bureaucracy, but disciplined continuity. The civilization stabilized its own internal reference frame. Consider the fragility of large projects today. Megastructures stall, budgets collapse, standards shift midstream, design revisions occur, even with digital tools. Yet here, 4,500 years ago, a 6 million-ton structure rose with geometric consistency across 2 decades. That is not primitive persistence. That is administrative durability. The pyramid required seasonal workforce mobilization, logistical continuity of quarry supply, transport networks, food provisioning, skilled stone shaping maintained across years, and supervisory hierarchy capable of maintaining standards. And most critically, a cultural commitment that the project must not deviate, which suggests something profound. The pyramid was not just a monument, it was a stabilizing force within the civilization. A project so central that its continuity was non-negotiable. Modern engineering models time as cost. But here, time was a variable to be controlled. Because every year introduces entropy, tools wear, knowledge diffuses, memory fades, personnel rotate. To prevent drift, the builders had to externalize knowledge, not merely in minds, but in systems. Possibly master baselines etched into bedrock, permanent reference markers, physical calibration rods, repeated celestial observations to refix north, and training protocols for apprentices. They did not need modern manuals. They needed repeatable procedure, and repeatability is the essence of engineering. Inside the pyramid, there is no moment where geometry wavers. No internal chamber misaligned because the original architect died. No upper course rotated slightly because a new team guessed wrong. No slope correction visible in casing remains. Instead, we see continuity. That continuity implies a project culture, an inherited standard, a shared geometric language that persisted across years and perhaps across reigns. Look at the larger Giza plateau. The Great Pyramid of Giza does not stand alone. Nearby rise the pyramids of Khafre and Menkaure. They too exhibit cardinal orientation. They too follow geometric discipline. This suggests that the measurement tradition was not a one-time event. It was sustained, which means the reference frame of Egyptian civilization, at least during the 4th dynasty, was extraordinarily stable. Stable enough to execute multi-decade geometric precision without deviation. That level of societal continuity is rare in human history. We marvel at 2.3 million stone blocks, granite beams weighing 70 tons, and sub-arc-minute orientation. But the most astonishing feat may be invisible. They held their measurement system steady for 20 to 25 years. No collapse, no redesign, no drift. The structure we see is not just stone stabilized to Earth's axis, it is time stabilized against entropy. Which raises a question that cuts deeper than any shaft carved through limestone. Because modern engineering preserves knowledge in drawings, manuals, digital models, and specifications. What did they have? Papyrus records do not survive at scale from that era. No detailed construction blueprints have been found, no comprehensive engineering manuals remain, and yet the precision endured. So we arrive at the next threshold. How do you maintain geometric fidelity across decades without written engineering manuals? How do you prevent drift when your knowledge lives in human memory? And if it was written, where did it go? Before we imagine cranes or modern lifting devices, we must return to the essentials. The tools in the hands of the men who carved and lifted the stones of the Great Pyramid of Giza. No steel, no pulleys of iron, no machines that could multiply human strength. Only the materials they could access: copper, wood, stone, sand, water. Yet even in this limitation, there lies the astonishing intelligence of their method. Copper chisels, sharpened against abrasive stones, were the primary instruments for shaping limestone and softer sedimentary rocks. They were relatively soft, easily worn, and limited in the size of incision they could make. Yet the Egyptians developed systematic techniques to extend their effectiveness. Large dolerite pounders, dense stones imported from quarries miles away, struck repeatedly to rough-shaped massive blocks. Laborers applied water to the cutting surfaces to reduce dust, cool the copper edges, and increase abrasion efficiency. Every strike, every shave was considered. Excess force could shatter the block. Too little force was inefficient. Precision, even with primitive materials, was embedded in every action. Transporting stone required the same meticulous approach. Wooden sledges moved across lubricated sand, the friction minimized by adding water to create a thin slurry. Experiments showed that this could reduce resistance dramatically, a practice mirrored in artistic reliefs depicting workers dragging colossal blocks. The sledges, simple in design, required careful attention to avoid twisting, tilting, or sliding of heavy loads. Stability was measured, checked, and corrected continuously. For surveying and measurement, the Egyptians did not rely on cords stretched blindly across the desert. Strings, while convenient, are vulnerable. They expand, contract, and sag. Even a 2% stretch over the pyramid's footprint, nearly 230 meters, would introduce errors that could accumulate catastrophically. They compensated by using wooden rods cut across the grain, which resisted warping and remained stable over distance. With rods, angles and lengths could be repeated with confidence. The choice of rods over cords is revealing. It demonstrates metrological intelligence, an awareness not only of the immediate task, but of how small errors compound. They understood that if every measurement carries a slight deviation, these deviations multiply across tens of thousands of placements. One misaligned block is small, but across hundreds of courses and millions of tons of stone, the effect becomes enormous. By choosing the right material, by understanding mechanical properties, the builders reduced error before it could arise. Their intelligence was embedded in anticipation. Every tool, every choice of material, every method was selected not for convenience or speed, but for its ability to maintain integrity under repeated use. The dolerite pounders could crack limestone without splitting it into unusable fragments. Copper chisels allowed fine trimming. Wooden sledges distributed weight predictably, while lubricated sand prevented drift during transport. Measurement rods preserved alignment. In every case, the Egyptians preemptively constrained the potential for failure. This constraint extended to their understanding of angles and leveling. Surveying instruments, simple in form, relied on the principle that repeated observation allows error to average out. They would check plumb lines, measure right angles using isosceles triangles, and cross-verify measurements with multiple methods. They did not trust a single observation. Redundancy, repetition, and calibration were baked into the process. The result is striking. Consider the casing stones of the pyramid, some weighing up to 15 tons. To shape, move, and set them with average joint gaps of 0.5 millimeter using copper tools and pounders required extraordinary patience and foresight. This is not brute force. It is precise application of mechanical understanding within the limitations of material science available to them. It is intelligence applied to constraint rather than freedom. Even the way they integrated natural bedrock demonstrates this mindset. The knoll at the pyramid's core was not removed entirely. Instead, its contours were incorporated into the design, its irregularities accommodated through precise measurement and adjustment. The builders observed the variability of nature and introduced correction systematically. No improvisation, no guesswork. Everything was measured, recorded in mental or physical reference frames, and translated into repeated reliable outcomes. Every tool, every method, every decision reflects an understanding of error accumulation, that the pyramid is not a collection of stones, but a system in which each element influences the next. A system in which one deviation, if unchecked, could propagate into catastrophic misalignment. The Egyptian solution was simple in its elegance: constrain the variables, choose stable materials, repeat measurement, and correct continuously. Precision arises not from the tools themselves, but from the disciplined application of method. It is tempting to look at copper chisels and dolerite hammers and assume a primitive culture laboring with inadequate instruments. But that perspective misses the point. They were not primitive. They were constrained. And in constraint, they found control. The limits of their technology forced them to think in terms of error, tolerance, redundancy, and verification. They were forced to codify process in action, embedding knowledge not in text, but in repeated practice, in the flow of work itself. Every rod laid out for alignment, every sledge slid across sand, every granite beam hoisted into relieving chambers reflects the same mindset. They approached execution as a system. Each act of labor was also an act of measurement, each stone a confirmation of method. Knowledge was expressed through doing, not writing. And it is this that transforms our understanding of the pyramid. It is no longer a monument merely to kingship or religious aspiration. It is a monument to applied intelligence, a testament to a civilization that mastered the interaction of material, force, and geometry. It is a structure where knowledge was not stored in ink or papyrus, but encoded in the discipline of its construction. So as we consider the tools, copper, stone, wood, remember this. These are not symbols of limitation. They are the instruments of metrological sophistication. They are the threads through which precision, repeated over decades, became enduring. And the haunting question remains. These men were not primitive. They were constrained. But what does it mean to master a system entirely through constraint? How far can knowledge extend when it exists only in execution, in method, in the disciplined repetition of labor across generations? Estimates suggest that around 20 to 30,000 skilled workers participated in the construction at any given time. This was not a permanent stationary crew. Labor rotated. Seasonal workers arrived during the inundation of the Nile when farming was impossible, supplementing a core group of full-time artisans. Each new cohort had to be integrated seamlessly into ongoing operations. Knowledge could not be lost as apprentices replaced veterans, or as foremen changed mid-project. The continuity of precision demanded management that anticipated human turnover. And management there was, explicit and hierarchical. Teams were organized by function: quarrying, transport, stone dressing, placement, survey, and supervision. Each team had a lead, each lead reported upward, and each action was nested within a larger plan that spanned decades. Instructions were likely communicated through demonstration, measurement, and verification rather than written manuals. Every worker became both a laborer and an instrument of control, embodying knowledge in practice. Blocks themselves were standardized. Limestone and granite were cut to repeatable dimensions. This allowed processes to be predictable, repeatable, and verifiable. Each stone could be expected to fit its assigned place, reducing uncertainty during placement and preventing error accumulation. Standardization at this scale is a hallmark of systems engineering, long before the term existed. It is an approach that considers not just the object being constructed, but the organization required to construct it reliably. The workflow was inherently modular. Teams could work on separate pyramid faces, on transport from multiple quarries, on internal chambers, without compromising the integrity of the whole. Each subsystem was coordinated to preserve the overall geometry. Disruption in one area could be compensated by adjustment elsewhere, but only because measurement standards were fixed and verified. The labor system itself was a stabilizing force, ensuring continuity across years, across generations. Imagine the logistics. Tens of thousands of workers, moving millions of tons of stone, feeding themselves, coordinating transport across miles of desert, yet without written schedules or modern communication tools. And yet they maintained a coherent pace, sustained by standardized procedures, by embedded measurement practices, and by strict hierarchies that allowed authority to propagate through the network. This was not a loose workforce. It was not a group improvising in the desert. It was a civilizational scale operation, where human labor was integrated into the structure itself. Each worker was a node in a network that preserved geometry, enforced baselines, and maintained alignment. The pyramid itself was the product not only of stone and measurement, but of human systems disciplined across decades. And therein lies the shift in perspective. We often admire the pyramid for its size, its stone, its alignment. But the truly extraordinary achievement is the human coordination behind it. This was applied systems thinking, a form of engineering that integrates people, processes, and materials into a coherent, enduring whole. The pyramid rises not only because of physical effort, but because of organizational stability, the ability of human networks to execute precise, repeatable operations over decades. When we consider the Great Pyramid, we must see it as more than architecture. Its foundations and angles are mirrors of social engineering. Its perfect slopes and seamless joints reflect the disciplined management of thousands of men. Every course laid, every granite beam set, every casing block aligned, depended upon humans functioning as both labor and mechanism. The labor system itself was a tool of measurement, a way of enforcing standards. Rotational crews ensured that no knowledge was lost. Supervisory hierarchies ensured that deviations were corrected. Standardized blocks enforced repeatable outcomes. Redundancy, repetition, and discipline created resilience against the unpredictability of human behavior. By understanding the workforce as a system, we begin to glimpse the true sophistication of the pyramid. It is not merely a collection of stones, nor simply a tomb, nor a symbolic gesture of divine authority. It is an infrastructure of knowledge in motion, a network of people, processes, and objects, all constrained to the same geometric logic. And this realization reframes the Great Pyramid entirely. Its value is not only in the stones or the angles, but in the coordinated execution of an entire civilization's capabilities. Precision at this scale is social as much as it is mathematical. Discipline is not merely measured in millimeters, but in the obedience of thousands of hands to a collective standard, maintained without error across decades. We are tempted to stop at awe for the stonework, for the granite, for the polished casing. But the deeper revelation is systemic. The pyramid is not simply a structure, it is a stabilized network where human organization, measurement, and method converge to create permanence. And now, as we consider this network, the question emerges with growing weight. If the pyramid is sustained by an entire civilization acting as a coherent, disciplined system, then what happens when the system itself falters? What does it leave behind when the network disperses, when the methods are no longer enforced, when only stone remains? Even in the desert light, the scale of the Great Pyramid of Giza overwhelms the senses. 230 meters per side, 146 meters high, millions of tons of stone stacked with extraordinary care. But as we look beyond sheer size, another layer of astonishment emerges. The relationship between the pyramid's base and its height. The ratio of its perimeter to its height aligns astonishingly close to a circle's circumference compared to its diameter. Not perfectly, but within a fraction of a percent. Scholars have debated whether this was deliberate. Did the architects of the Fourth Dynasty understand the mathematics we now call geometry? Or is this merely coincidence, an emergent property of building a massive structure with consistent slopes and angles? Perhaps they did not consciously encode the abstract concept of a circle's ratio. Perhaps they did not intend to transmit a symbolic message to the future. Yet the fact remains, the pyramid rises in a proportion that mirrors an ideal mathematical relationship almost perfectly. Even setting aside deliberate symbolism, the mere construction of such a ratio requires extraordinary consistency. Every face of the pyramid must maintain the same slope from base to apex. Each course of stone must replicate that slope. Even the smallest deviation accumulates. By the time the apex is reached, an error of a few millimeters at the base could become a catastrophic misalignment. The builders had to maintain not only straightness, but proportionality across millions of tons of stone, ensuring that every course reinforced the intended ratio. This is not a trivial observation. Consider the difficulty of enforcing a single angle consistently across hundreds of layers. Each layer was built by different teams over many years under varying environmental conditions. Temperature, wind, and sandstorms could subtly alter measurement. Materials themselves are imperfect, yet the finished pyramid shows uniformity that would challenge modern construction without digital modeling. The statistical probability of achieving such proportionality by chance is vanishingly small. It is here that we must shift our understanding of knowledge. The pyramid does not contain equations etched in stone. It does not present a theorem for students to decode. There are no written instructions, yet the builders enforce principles as rigorously as any classroom demonstration. The consistency of slope, the proportional relationship between base and height, the alignment to cardinal points. These are all manifestations of understanding applied, knowledge made real through execution. This is the silent argument of the pyramid. Knowledge need not be symbolic to exist. It can reside in the discipline of labor, in the repeatable application of method, in the maintenance of standards over decades. Every block set in place, every casing stone polished, every internal chamber aligned, reflects comprehension encoded in action, not in language. The more we examine this proportional consistency, the more it becomes evident that the pyramid is a study in control. Its design enforces regularity through material reality, not through abstraction. The proportions are not accidental, even if they were not consciously intended to convey mathematical truths. They are the necessary outcome of meticulous geometric enforcement, a disciplined system in which every measurement supports the next. Every slope maintains the intended angle. Every course contributes to a consistent whole. Here, precision and scale meet. Scale alone is unremarkable. Monumental structures exist across history. But to build monumental scale while preserving proportion across millions of stones is another order of difficulty entirely. The probability of achieving this by uncoordinated labor is effectively zero. Only a system designed for repetition, verification, and correction can produce such uniformity. And so the pyramid speaks in a language of method. Its message is not found in inscriptions or carvings. Its message is written in the relationships between its stones, in the exactness of its slope, in the alignment of each course with the next. It is proof that a civilization understood consistency and enforced it not with abstract symbols, but with the reality of executed work. As we step back from the edges of the base and trace the slope to the apex, we begin to see the philosophical consequence. This is knowledge as action. Knowledge expressed through the medium of stone, through the discipline of labor, through the fidelity of measurement maintained over decades. It is knowledge that cannot be stolen, cannot be misread, cannot fade with ink or papyrus. It exists because it was applied, because it was repeated, because it was made tangible. And so the pyramid leaves us with a paradox. Its builders may not have been calculating the ratio consciously in the terms we now understand. Yet through process alone, through enforced geometric discipline, they achieved what is mathematically extraordinary. Knowledge does not need to be symbolic to be real. It can exist silently, embedded in execution, living in the very reality it creates. And when we realize this, we must ask ourselves, what other forms of knowledge throughout history might have been expressed not in writing, but in doing, in constructing, in imposing order upon the world? As we peer into the hollow heart of the Great Pyramid of Giza, one fact strikes more profoundly than any stone. There are no engineering texts, no scrolls, no diagrams, no papyrus instructions detailing how to quarry, transport, cut, or place millions of blocks with millimetric precision. The ancient scribes of Khufu's time left us letters, accounts, perhaps tax records, but nothing that tells us how to replicate the pyramid's perfection. Contrast this with civilizations that followed. Centuries later, the Greeks, Romans, and medieval engineers documented rules for arches, domes, aqueducts, and cathedrals. Manuals, treatises, and codices preserved ideas so that knowledge could be transmitted across generations, even when practitioners were long dead. Writing stores memory, captures thought, encodes abstraction. It allows a distant student to study the principles without touching the materials themselves. But the Egyptians of the 4th dynasty, it seems, chose a different medium. The Great Pyramid itself is the message. Execution replaces exposition. The knowledge was not stored in words, it was preserved in process. In the precise arrangement of millions of stones, in the alignment of axes, in the uniformity of slope and joint. The builders did not write their methods, they applied them. And by doing so, they encoded capability, the ability to repeat, to maintain precision, to integrate human labor with massive material reality. This distinction is profound. Writing preserves abstraction. Execution preserves effect. A drawing or a scroll can survive intact, but it cannot enforce itself. The pyramid, in contrast, is self-verifying. Every course of stone rests upon the previous one. Every beam supports weight above it. The method is embedded in the material. It cannot be misinterpreted or forgotten. If the process deviates, the consequences are immediate. The structure fails. In this sense, the Great Pyramid is a living record of applied knowledge. Consider the implications. Engineers today rely on documentation, drawings, specifications, schedules, digital models. These capture ideas. They tell what could be done. The ancient Egyptians bypassed abstraction. They created a monument that demonstrates knowledge through reality itself. To understand their capability, one need only observe the outcome. The precision, scale, and coherence of the pyramid testify to a civilization that mastered application, not explanation. And this mastery was not a one-off achievement. Every facet of the pyramid, from the base leveling to the alignment of the king's chamber, from the slope of the casing to the hidden relieving chambers above, preserves capability across decades. This is the genius of method. It endures as long as the structure endures. Unlike ink, which fades, tears, or is destroyed, constraint, the discipline of measurement and process, leaves its mark on stone, immutable and enduring. It is worth reflecting that this approach carries an elegance and a subtlety absent from written instruction. When you write a manual, you assume literacy, interpretation, compliance. Execution stores resilience. The next generation need not understand the theory fully, they need only follow the process. Measurement, alignment, repetition, verification, these do not require reading. They require discipline, observation, and adaptation. In this way, knowledge transcends language. Yet the silence of writing also leaves us with a paradox. Without records, the methods are opaque to us. Modern engineers can reconstruct theories about leveling, alignment, and material handling, but certainty remains elusive. The methods survived because they were applied rigorously, not because they were explained. We see the capability, not the instructions. We infer the system, not read it. This silence challenges our assumptions about what knowledge is. We often equate learning with reading. We measure intelligence by the texts a culture produces. But here, in the pyramid, the lesson is inverted. The most advanced knowledge is not what is written. It is what is enacted, what is enforced, what leaves a lasting effect on the world. The stone speaks, the angles speak, the centerline and relieving chambers speak. And it asks us a question as stark as the desert sun. Which endures longer, ink or constraint? Words crumble, paper rots. Knowledge in text requires continued interpretation, but knowledge in execution becomes reality. It resists time. It survives neglect. It survives revolutions and collapses of authority. The pyramid itself is proof of this principle. By embedding method into the very bones of the structure, the Egyptians ensured that what mattered most, capability, could outlast any pharaoh, any scribe, any dynasty. And yet, as we stand before this silent edifice, a deeper tension arises. For all the knowledge it preserves, it cannot speak. It cannot tell us how it was done. Only that it was done. Only that the civilization understood the subtle interplay of measurement, labor, and material. Only that method, when maintained with discipline, can create effects far beyond the reach of mere text. We can measure the angles, weigh the stones, calculate the volumes, and trace the labor networks. But the pyramid refuses to give away its methodology in language. It insists we understand through observation, deduction, and reflection. It forces us to confront the reality that knowledge is not solely ideas. Knowledge is action. Knowledge is constraint. Knowledge is preserved in the very fidelity of execution, held steady across decades, across generations, across the unrelenting passage of time. After the Great Pyramid rose, gleaming in Tura limestone and aligned to the cardinal points with sub-arc minute precision, the trajectory of Egyptian monumental construction shifted. The succeeding pyramids, though still immense, reveal a subtle but telling decline. Their angles waver slightly. Their casing stones lack the mirror-smooth continuity of Khufu's. Some courses are uneven, blocks are misaligned. Where Khufu's pyramid enforced discipline at every layer, later structures reflect a relaxation of method, a creeping tolerance for error. This decline is instructive. Precision is not a natural byproduct of building. It is not inevitable, it is maintained. Every perfectly level base, every true corner, every accurately inclined casing stone at Giza required active management. It demanded oversight, calibration, verification, and adherence to standards across decades. When any part of that chain is neglected, when reference frames drift, errors multiply. Small deviations become perceptible, then structural, then catastrophic. The evidence is unmistakable in the architectural record. Later pyramids experienced failures that Khufu's did not. Some collapsed partially, others were left incomplete. The lesson is societal as much as architectural. Maintaining such a baseline of precision is not merely a matter of technical skill. It depends upon institutional stability, continuity of leadership, and cultural commitment to measurement. Khufu's pyramid reflects a civilization in which these conditions were aligned: a centralized authority, stable administration, trained artisans, standardized tools, and a shared understanding of geometric principles. Remove one of these pillars, and the system begins to degrade. Over time, political turbulence, resource depletion, or shifting priorities eroded the mechanisms that had preserved the baseline. Later kings may have lacked the authority to enforce exacting standards, or perhaps the cultural imperative to maintain perfect geometry diminished. Each pyramid constructed afterward shows the consequences: misaligned faces, irregular slope angles, casing stones that no longer fit perfectly, interior chambers with uneven floors. The decline is subtle at first, almost imperceptible, but becomes unmistakable when compared with Khufu's near-flawless model. This illustrates a profound point. Mastery of knowledge is fragile. It is not merely knowing what to do, it is maintaining the fidelity of execution across time. A civilization may possess expertise in theory, in tools, and in labor, but unless the reference frame of measurement, process, and oversight is preserved, precision unravels. Human systems drift. Processes that are not actively enforced degrade. And in architecture, as in society, small drift accumulates into visible failure. Khufu's pyramid stands as a benchmark, a demonstration that when a civilization stabilizes its reference frame, its standards, procedures, and governance, extraordinary precision is possible. Later pyramids reveal the converse. When baselines slip, even immense effort cannot reproduce the same exactitude. Perfection was never automatic. It was achieved and maintained deliberately. The contrast is stark. It warns that knowledge embedded in execution is powerful, but not indestructible. It requires constant reinforcement. Systems decay, standards fade. Without vigilance, what once was exact becomes approximate. Civilizations, like buildings, suffer from the drift of their own baselines. And now the question arises, hanging as sharply as a corner joint in a misaligned pyramid. What changed? What combination of political, cultural, or technical factors allowed precision to deteriorate after it had once been so extraordinary? The answer lies not in stones alone, but in the shifting systems that controlled them, in the human networks that once enforced order, now quietly unraveling. The Great Pyramid does not whisper of gods or legends, though countless generations have tried to read it that way. It does not recount myths, nor does it encode hidden prophecies. Instead, its language is unambiguous, tangible, and precise. The pyramid reveals a worldview. Every stone, every angle, every casing joint is a testament to an approach to reality that privileges measurement over conjecture, stability over whim, and constraint over chaos. Khufu's architects understood that knowledge is expressed through control, through method, through the disciplined repetition of process. At the core of this worldview is measurement. Every baseline, every slope, every internal chamber was defined, verified, and maintained. They did not trust approximation or guesswork. The base was leveled to millimeter tolerances, corners formed near perfect right angles. Alignment to true north required repeated observation of celestial phenomena. Measurement was not an afterthought. It was the medium in which understanding was expressed. Alongside measurement comes constraint. The builders worked not with infinite freedom, but with deliberate limitations. Copper chisels, dolerite pounders, wooden sledges, tools that are rudimentary by modern standards, became instruments of incredible precision because their use was governed by rigorous methods. Constraint enforced discipline. Constraint controlled error. Constraint converted human effort into exactitude. It is in these limitations, paradoxically, that creativity and intelligence flourished. This worldview emphasizes stability and repeatability. Construction spanned decades. Workforce rotation, tool wear, seasonal interruptions, and political flux could have introduced chaos at every step. Yet processes were designed to resist drift. Standards were preserved, methods were repeatable. Each stone, each course, each chamber reinforces the next. The knowledge embedded in execution survived time because the system was anchored, not in individual brilliance, but in institutionalized continuity. The pyramid aligns itself to physical constants, the rotation of the earth, the pull of gravity, the level of bedrock, and the immutable logic of geometry. It encodes no stories about the afterlife. It does not attempt to depict the cosmos in symbolic form. Instead, it demonstrates a civilization that oriented itself according to what is real, what is measurable, what can be verified. Level surfaces, right angles, consistent slopes, and cardinal alignment are the vocabulary through which knowledge was expressed. This is a reality-first philosophy. Myths, imagination, and symbolic storytelling have their place in culture. But the pyramid asserts another kind of truth, that stability and precision, discipline and method, are the pillars upon which monumental achievement rests. Its design is not allegorical, it is operational. Its message is not read, but observed, measured, and internalized. The worldview encoded here is practical yet profound. It says that the universe has rules, and to act effectively within it requires alignment to those rules. By studying Khufu's pyramid, we glimpse the priorities of its builders. They valued calibration over ritual, repeatable procedure over improvisation, and the anchoring of work to enduring constants over fleeting authority. They did not merely carve stone, they imposed order on chaos, not as an exercise in symbolism, but as an application of knowledge. Their worldview was disciplined, systematic, and deeply attuned to the measurable world. And yet, standing before this ancient monument, we confront an existential reflection. The pyramid is anchored to the constants of the earth and the cosmos, but what of us? In our own civilization, in our own constructions of knowledge, in the structures we rely upon, what do we choose as our anchor? Are we tethered to stable measurement, to enduring principles, to methods that resist drift? Or do we rely on ephemeral symbols, shifting belief, and narratives untethered from reality? The question lingers, as silent and immovable as the stones themselves. If the Egyptians anchored themselves to the physical world to achieve greatness, what is our anchor in a world where so many reference points are slipping? where knowledge is stored in transient media, where execution is divorced from understanding. When we speak of the Great Pyramid, the popular imagination leaps to copper chisels, massive ramps, and the brute strength of tens of thousands of laborers. These are easy answers, tangible and dramatic, and they have shaped millennia of speculation. Yet none of these alone explains what makes Khufu's pyramid so extraordinary. Copper tools can be sharpened or replaced, ramps can be reconstructed, labor can be mobilized. And yet, as the archaeological record demonstrates, no later civilization, with access to all these same resources, has managed to replicate the precision, the scale, or the enduring stability of that structure. The secret does not reside in tools, materials, or manpower. The secret lies elsewhere in something far subtler, far more profound. The lost technology, if it can even be called technology in the sense we understand it today, is the mastery of repeatable geometric process control sustained across decades. The builders of Khufu's pyramid did not merely place stones. They created an entire framework, procedural, hierarchical, and methodological, in which every measurement, every placement, every alignment could be repeated reliably over and over again, without drift. They understood that a small error in one location, compounded across hundreds of layers and millions of tons, could unravel the integrity of the entire structure, and so they constructed systems to prevent such drift, systems that were maintained rigorously across years, across generations, and across shifts in leadership. This required centralized stability. It is easy to underestimate the social and political dimension of the pyramid's precision. A structure of this magnitude, designed to last millennia, demands continuity not just in tools or skill, but in vision and authority. The Pharaoh's administration had to ensure that measurement standards were enforced, that teams of laborers maintained their procedures, that surveyors validated the baseline, and that oversight persisted across decades. Stability here is as much organizational as it is technical. Without it, even the most brilliant processes would fragment and precision would decay. Khufu's pyramid demonstrates a level of civilizational coherence that allowed method to survive longer than any individual human lifespan. Embedded in this continuity is error correction. The pyramid's builders recognized that even small deviations are inevitable in a project of this scale. They designed feedback into the system. Surveyors would verify the positions of stones, check angles, and adjust as necessary. Ramps, sledges, and pulleys were not used haphazardly. Their use was informed by constant observation of results. In essence, the construction site was a dynamic system. Measurements were taken, deviations were noted, corrections were applied, and the process repeated. It is a proto-engineering principle that anticipates modern quality control long before the term existed. At the core of all of this was measurement discipline. Every action was subordinated to a standard, a baseline, a frame of reference that remained invariant across space and time. The base of the pyramid leveled within millimeters, the sides aligned within a few arc minutes of true north. The slopes maintained consistently across hundreds of layers. These are not accidents. They are the products of sustained, deliberate attention to measurable reality. Knowledge was embedded in practice. It was preserved not in papyrus, not in ink, not in abstraction, but in the structure itself. This is the true lost technology, the capacity to maintain a civilization-scale process where method, measurement, and correction are enforced with consistency over decades. It is a combination of systems thinking, organizational coherence, and applied geometry that has no direct analog in the archaeological record. Later civilizations could copy the outward forms, the pyramid shape, the general slope, the monumental scale, but they could not replicate the internal logic, the discipline, the feedback systems that produced Khufu's enduring precision. These are not lost in the sense of a stolen secret. They are lost in the sense that the social, cultural, and institutional conditions that supported them no longer exist. Consider the implications. Modern engineering often relies on digital tools, CAD models, precise sensors, and standardized protocols. Yet even with computers, laser levels, and advanced materials, achieving the same combination of scale, stability, and precision without ongoing oversight would be impossible. The Egyptians did it with copper, stone, wood, and disciplined process alone. They understood error accumulation, they enforced tolerance limits, and they embedded knowledge in repeated action rather than in textual abstraction. Their system was resilient, scalable, and self-reinforcing. The Great Pyramid is, in this sense, a monument not just to stone, but to civilization-level process control. Its precision is a reflection of a society that could enforce discipline across generations, that could maintain standards despite environmental and political challenges, that could encode knowledge in practice rather than in symbols. And because it was encoded in the structure itself, it persists even when the civilization that produced it has faded. The pyramid endures, silent but eloquent, a record of what is possible when method is prioritized over whim, when constraints are respected, when precision is institutionalized. And yet, as we marvel at this achievement, a shadow falls over our understanding. For all its endurance, the lost technology is vulnerable to the very fragility it sought to overcome. Repeatable geometric control, centralized stability, error correction, measurement discipline, all these require active maintenance. Systems drift, baselines shift, oversight diminishes, and human institutions collapse. When these reference frames fail, precision is lost. Monuments crumble, methods are forgotten, and what was once replicable becomes irrecoverable. The lesson extends beyond pyramids. It is a warning for every civilization, past and present. Knowledge that exists only in execution is powerful, but it is not invulnerable. It depends upon the integrity of the system that maintains it. The Egyptians achieved what they did because the reference frames of labor, measurement, and authority were coherent, enforced, and continuous. Remove the enforcement, allow the reference frame to collapse, and the same methods cannot be reliably applied again. We are left with a haunting thought. Khufu's pyramid stands not merely as a marvel of architecture, but as evidence of a civilization that mastered the maintenance of reality itself. It shows us the possibilities when humans align social structures, processes, and measurement standards over time. But it also poses an existential question. What happens when those reference frames collapse? When authority falters, methods are neglected, and baselines drift, does knowledge vanish with them? Or does it persist in some hidden, encoded form, waiting for the next civilization to rediscover it? And so we confront the final paradox of the lost technology. It is at once eternal and fragile. Eternal in the sense that the pyramid remains, an indelible imprint of applied knowledge. Fragile in the sense that the systems that created it are easily destroyed, leaving future generations to marvel at an achievement they cannot hope to replicate without restoring what was lost. The greatest technology of ancient Egypt was never copper, never ramps, never manpower. It was process, discipline, method, constraint. And the haunting question lingers. When reference frames collapse, what survives? We have walked through stone and time, traced the angles and slopes, measured the shadows of the Great Pyramid, and seen the invisible lines that guided its construction. And now, at the summit of understanding, we confront the ultimate truth. The pyramid does not contain hidden secrets. It does not whisper coded messages, divine prophecies, or cosmic instructions. Its message is far subtler, far more profound. The Great Pyramid is a demonstration of method, a frozen record of process control applied at civilizational scale. It is knowledge made real, not written down. It is the material expression of a society that treated reality as a framework to be respected, constrained, and mastered, rather than a canvas for speculation or whim. Every block, every joint, every precise alignment tells the same story. Reality is disciplined. The angles were not approximated, the slopes were not guessed. The base was leveled to millimeters, the orientation fixed to true north, the interior chambers aligned to axes and planes with care that rivals the most sophisticated modern engineering. These were not accidents. These were the outcomes of repeated procedures, error correction systems, and hierarchical oversight maintained consistently over decades. The pyramid itself is the artifact of a civilization that understood that the universe has rules and that to act effectively within it requires alignment, repetition, and fidelity to measurable truths. It is here, at the confluence of ancient and modern thinking, that we recognize the continuity of human endeavor. Our contemporary world depends upon stabilized baselines, just as the Egyptians did. Atomic clocks, GPS satellites, engineering calibration systems, financial ledgers, and digital infrastructure all rely on the same principle. Without consistent reference frames, systems fail. In this sense, Khufu's builders anticipated a truth that is more relevant now than ever. Civilization rises not merely by ideas, invention, or ambition, but by disciplined measurement, by anchoring action to enduring, verifiable standards, and by enforcing precision across human networks. The pyramid teaches that control is not achieved once, but must be maintained. Baselines drift, leadership falters, societies change. The Egyptians preserved theirs across generations through governance, training, and methodical execution. Today, our baselines are maintained through institutions, technology, and protocols, but they are no less fragile. When they drift, when calibration fails, when measurement is neglected, chaos emerges. Infrastructure collapses, systems break down, and the illusion of permanence vanishes. And so we return to the philosophical reflection that frames the entire journey. The pyramid is not a monument to belief. It is proof that disciplined interaction with reality produces results that endure far beyond the ephemeral span of human life. It is a civilization's alignment with the physical world, a record of what is possible when constraint is respected, when process is repeated, when error is anticipated and corrected. It is method made monumental, knowledge rendered permanent in stone. The final question is stark and existential. If our own reference frames weaken, if the systems that stabilize our society and preserve our knowledge begin to drift, what will remain standing? Will it be our stories, our myths, our symbols, and intangible and fleeting? Or will it be only that which we have aligned to reality itself, the enduring structures, processes, and principles that can withstand the passage of time and the erosion of authority? The Great Pyramid, immovable, silent, precise, and eternal, offers an answer without speaking a word. It teaches that civilizations do not rise by belief alone, nor by imagination alone, nor by strength alone. They rise by discipline, they rise by measurement, they rise by the conscious, repeated application of method to reality. And if we fail to uphold our own reference frames, if we allow drift and neglect to unravel our baselines, we may discover that all else, all our stories, our plans, our ambitions, is transient. Khufu's pyramid will endure. It endures not because of myth, not because of legend, but because it is aligned with reality. Perhaps our challenge in the modern age is to learn the same lesson, to align our own systems, our own knowledge, our own civilization to what is real, what is verifiable, and what can survive the test of time. Only then can we hope that what we build will endure as this ancient monument endures, silent, exact, and unyielding, a testament to disciplined thought applied with precision and care. And as the desert wind sweeps across its polished stones, as the sun casts perfect angles upon its faces, we are left with one final quiet question. When the frames that support our world begin to wobble, when the baselines that guide our civilization falter, what will be left standing? Our stories, or only that which we have truly aligned with reality? The pyramid offers no words, only the permanence of stone. And in that permanence lies the elixir of understanding, the lesson of alignment, discipline, and the enduring power of method. Thank you for joining us on this extraordinary journey through the universe on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us where we unravel the darkest mysteries of space.